Welcome to everybody who's joined us for the first of our additive manufacturing roundtables, or our roundtables around advanced manufacturing. And we're lucky enough to have three very experienced presenters in this sector around additive manufacturing. I'm Anna Murray. I'm the National Territory Manager of CAPRO Australia. I will talk a little bit more about CAPRO in a minute. So just to let you know, first of all, I'm just going to start off with some brief introductions, and then we're going to launch straight into John's presentation, The Changing Face of Manufacturing. And after that, we'll be followed by Peter Rogers from Autodesk, talking about leveraging software to win in additive. And finally, Alex Kingsbury from RMIT will be talking about the role of research in your additive journey. So what I'd like to ask everyone to do is, if you have some questions as we go through the presentations, please put them in the chat box or the Q&A, and we have some time at the end of the session where we will just sit our three presenters up in a panel and we'll address any questions and queries that you have. So please jot them down, put them in the Q&A and chat as we go through the presentations, and we're going to sit down at the end and address them all. Briefly about CAPRO, we're a New Zealand-based company, owned and operated out of New Zealand for 25 years. We've been open here in Australia for nearly a year, and we're obviously an Autodesk partner and reseller, and we offer solutions services around the Autodesk solution set. And here, obviously, we're going to be focusing on the design and manufacturing side. So here's just a little group shot of the team. I think we're actually up to 30 now, but we offer a range of consulting services, technical support and training around the Autodesk software and others. And with no further ado, I am now going to hand over to John.
Thank you, Anna. Thank you. I'll get up and start sharing my screen.
Yeah, it's a little bit tricky, but once you can get going. Yes.
We can all see that okay?
Yep.
Yep. All right, excellent. Probably just give you a very brief, hopefully, as you know, I'm a bloody talker, so, you know, pull the hook out if you need to. My journey started back in 1991, seeing probably one of the first Stratasys machines operating in Swinburne, and I can still remember I saw it as clear as day, and I turned to the gentleman who was showing me the piece of kit, and I said, "Do you realise you're actually watching the future of manufacturing?" Anyway, I said, "It just won't be polymers, it'll be metals and ceramics and glass. It will touch all industries." And I remember this gentleman looking at me as if I had two heads. Anyway, from there, I purchased, I had a company called Interact Plastic Services, and we purchased the first machine into Australia into private business, which is a Stratasys FDM 1650. And as a lot of people said to me through the years, the problem was I was a little bit too early and industry wasn't ready. So that piece of equipment cost me $250,000 back then. And of course, now the costings have come down a little bit. But that just gives you a brief, and you'll understand why my passion is around additive. And probably to start off, instead of moving straight to the hub, I'd like to talk about just some of the processes that are available and some of the acronyms, only for those of you who are looking at this webinar and are still trying to understand some of the wording around some of the processes. So we'll move in, and the first one, of course, is the FDM, the fused deposition modelling, or the freeform filament, the FFS. As FDM was a trade name of Stratasys at the time, and it's, as the name suggests, it's a material, it's a polymer filament that's pushed through and then heated and being extruded through to a nozzle on a platform, and it builds in the XY direction and it solidifies just prior to the next layer being applied. And I'd say it was the technology is one of the most recognisable forms in 3D printing, although SLA was up at the time as well. SLA, of course, stands for stereolithography, which is a process that was commercialised by 3D Systems back in 1998. SLA uses, of course, an ultraviolet laser directed onto a vat of photopolymer resin. And it's heated to a liquid state, and the UV laser directed down onto the platform in the submerged vat of resin. The laser solidifies the resin layers according to the CAD file or the slice file that's been produced. The next one, of course, is laser sintering. SLS was a vat of powder. It had a rake that moved across to form each layer, and that's a laser hitting the powder, and that solidifies again in each layer. Digital light processing, which is DLP, very similar to SLA, although it's a light source, either light emitting diodes or an arc lamp. Again, it's applied through mirrors at the bottom of the photopolymer and slowly forms the product in the polymer as the actual bed moves upwards. Binder jetting. Binder jetting, there's quite a few variances now in binder jetting. I mean, if you look at multi-jet, and that it's HP have got them, X1 have them as well. So again, it's a material that's raked out over the build volume in a thin layer. Instead of being consolidated with a heat source, the binder jet head crosses over with a binder jetting material, not polymer, sorry, but a binder jetting substance over the surface, and it starts to bind it together. And when the complete platform lowers and the fresh layer of powder, of course, is raked across, and then the print head moves again. It's very similar to 2D printing, and it's formed by quite a lot of droplets that are jetted at a time. Select laser melting, SLM, again is virtually very similar to SLS, except this is a laser solidifying most commonly metals. So this is one of your metal printers onto a powder bed. It's fused direct metal laser melting and the select laser sintering. The laser powder bed is systems use a metal powder, of course, as feedstock. The powder is raked across the build platform, and the CO2 laser melts each layer according to the 3D slice file. The melted layer solidifies and joins to the layer below, forming the solid object. Once the layer is completed, of course, the build platform drops to the exact depth, and a new layer is raked over approximately 30 microns. Electron beam melting. Electron beam powder systems use a metal powder as a feedstock, again, similar to the laser powder bed systems, but the powder used is slightly larger in diameter, being approximately 50 microns. The powder is raked across the build platform, and the electron beam melts each layer according to the CAD file, and as the layer solidifies and joins to the layer below, very similar to what we've just spoken about. Blown powder and cold spray, they're two systems, blown powder systems that can be divided into two categories, one with directed energy and the gas dynamic spray or cold spray. Both work with a spray of metal powder towards the surface, but have different bonding mechanisms. Directed energy systems typically use laser or consolidate sprayed metal particles into the layers. These systems, of course, can be used for creating freeform objects. An object constructed layer by layer using the directed energy AM method, or can be applied as a coating or build up as an additional feature to existing part or substrate, often traditionally manufactured, such as repairing turbine blades. Some directed energy systems are contained within the sealed inert atmosphere, hence are suitable for reactive materials. One of the last that I'll go through, of course, is the wire-fed system, or WAM. Wire-fed systems use a metal wire as a feedstock and a thermal source to melt the wire. A freeform objects can be built by adding layer on layer of the melted wire. This process is much like traditional welding processes, but instead of using it as a joining technology, it's used to make whole objects. I won't bother reading all the way through it. And here we come to a little bit about the hub. The hub vision is to provide an industry-driven collaborative network of organisations that will foster growth and in the additive manufacturing sector. I look at it as the AM Hub is really the catalyst in bringing together the service providers, the technology providers, research institutes. That is a bit of a pet of mine as well, because I think after working several years with Bosch and working with industry and institutions in Europe, they work so well together, and we need to develop and foster that moving forward with our own manufacturing. Of course, looking at government mechanisms, which I'll talk a bit about later, being grants and that, and of course, as I said, the research institutes. Just to give you a bit of a rundown, AMTL has established the Additive Manufacturing Hub in partnership with the Victorian State Government. It was put in place to help Victorian business with breakthrough of additive manufacturing. It was officially launched in September 2018 and is delivered by AMTL and supported by a $1.85 million Victorian government grant. They knew that 3D printing, of course, is a game changer for manufacturing, is, of course, considered as a large part of the digital revolution, which the government, of course, is backing the technology so more local companies can now reap the benefits of what's available. Probably to let you know, the hub is put in place. It's really an enabler, a facilitator, and an educator to try and educate industry all around the value of additive manufacturing and how it can be incorporated with their own manufacturing processes. The hub there, of course, is to improve the access to Australian companies and to partly Victorians' world-class additive infrastructure and promote Victoria nationally as the global significant destination on the AM investment. The key activities, of course, of the hub will be to address identified skill gaps within the industry, developing capability in areas such as business case analyses designed for manufacturers through our natural network of registered service providers. The hub's there for all businesses and individuals to participate in, and happy to talk to anyone who wants to discuss that after the presentations. The main points of the hub, and I call it the 10-point plan. We've added an extra one, which is a little bit what I call my pet one, but it's there as a communication to provide an open forum of communication around additive, to expand the knowledge base of additive, or the AM sector, and what's happening globally, implementation, to implement AM technologies and techniques. Research, again, this is working with not just our industries here, but also our universities and research centres, helping to foster collaboration between both in areas of AM. Networking, of course, as some of you may realise, AMTL run or host at least nearly 40 events during the year, and that's a normal year, of course, not a COVID year. But we've started the events all again, and of course AMTL run probably the largest manufacturing expo in Australia, which is the AusTech exhibition, and now the AMW as well, which is actually been moved now till March 2022. Investment, of course, is to accelerate the uptake of the AM technologies, support in creating high quality additive manufacturing jobs, and that's also to look at developing further skill sets within our national area to help with industries who are taking up additive. Marketing, of course, is another big area for us. Again, we do a lot of marketing through the AMT magazine as well as a lot with social media. Sustainability, that's my pet one. The hub needs to become a sustainable model, and we're looking at that coming to fruition this year. There'll be more on that as we move forward, probably between June and August. Partnerships, we're there to help foster and develop local and international partnerships. And of course, I suppose the major one is adding value to delivering services that adds value to our members. Some of the top 10, or I believe some of the top 10 challenges in additive at this point in time is, of course, the investment costs that go along with additive, the knowledge gap, and that the knowledge gap is industry's understanding of where additive and that can fit within their own manufacturing processes and how it can be developed as a justifiable model. Of course, as I mentioned, the lack of skilled resources is a big area that we're trying to address, and we're working together with several institutions across the globe, one the John Barnes Group, and also the other one with ASTM. Post-processing is another big area of where additive has a hurdle in the adoption. Although, again, some of the methods that are coming out, we've just run one through the BIB voucher, is going to come out in the very near future, which will help with reducing times and that in post-processing. The lower penetration of advanced manufacturing technologies, and I look and feel very closely that Australia, we're about 10 years behind at this point, so we need to try and foster further penetration of the AM technologies. Weak participation in global supply chain markets, that's become evident, and that's become evident talking to quite a few of our primes, such as BAE, Boeing, as a couple of them. Weak participation in the global supply chain, as I indicated, lack of national level industry platform to voice concerns and influence policymakers. That's part of what the hub is trying to put together, is to become the voice of the members, I suppose, in approaching government for further government assistance and grants, and the lack of holistic additive manufacturing strategies to drive the industrialisation across the industry sectors. We did, as I said, we were started by a $1.85 million grant from the state government, or the Victorian government. This was also incorporated a BIB voucher, or Build It Better voucher system. That has really been a positive uptake, and unfortunately it was centred around Victoria. We're looking now at nationally, so stay tuned. This will be happening in the not too distant future. But what happened was, from a $1.3 million partnership with industry and government, it's actually, we've had 42 projects to date out of 55 applications, and to date that's generated 23 million within those 42 projects, and it's expected by June to have achieved over $26 million of investment that's been done. The BIB projects, I mean, as I indicated earlier, have come across a wide range of industries: medical, mining, fashion, aerospace, signage, defence, food and meat, rail, agriculture, housing, and others. And there's been some wonderful vouchers that have really taken off in that area. We've run dozens of knowledge transfers, events, webinars, technology showcases. We've published a lot of case studies. If you jump onto our website, you'll get to have a read of some of those. And of course, as I mentioned earlier, with skills or building the skill sets, we have linked with John Barnes Group and the ASTM internationally, formerly known as the American Society for Testing and Materials. It's reached out to the hub, and of course now we've got accreditation training sessions that have been brought online through to the Australian industries here. Just some of the things that have come out of the project, and listen, I'm not going to, I haven't brought Coke or popcorn to this, so I'm not going to go into the full talk about this, but where some of the things that have come out, Shock Sport helmets have developed a helmet now that is being widely taken up by the American football. It's really developed into a very large project. Advitech Lighting, they've done a lot around the mining industry of developing lighting now that is going into mines that we don't have the problem with spark or anything that could cause explosions. X-Rotor, well, that's been another good one working in the defence area. He's developed rotors on the drones now that are noiseless. And another big mining operation out of South Australia is interested in the product from Gasmic. They've produced a new blasting system that is very easily installed, taking it from 20 minutes to install each system down to 5. So again, this is just some of the things that's come up. They've actually got an $11 million order, and a lot of interest now coming from overseas, from South America and also Africa. I think that takes in exactly what the hub's been doing over the past 2.5 years, and we're hoping that this is now going to grow even further. It will and is slated to be the national hub, and will be supported by a lot of the major primes, BAE, Boeing, to name a few. And we're also talking to some other areas as well. I think that takes just about care of what I've got to talk about. Hopefully you've found some interest in what I've presented. So I'd like to say thank you, and thanks a lot, Anna and CAD Pro and Autodesk for inviting me along to talk.
Thank you very much for that, John. And I'm encouraging all the audience to think of your questions, put them in the Q&A or the chat, and we will address them at the end. We'll have a bit of a panel, and I've been assured that everybody's going to switch their video on for the panel. Now I'd like to hand over to Peter Rogers from Autodesk, who's going to talk about leveraging software. So handing over to you, Pete. Thank you.
Yeah, thanks, Anna. How are you going, guys? Just want to confirm, you guys able to see full screen at the moment?
Yep.
Yeah, perfect. Okay, so again, today we're going to be talking about the software role in the additive process. A little bit of background on myself. So again, as Anna kindly introduced me, so my name is Peter Rogers. I work for Autodesk. I am the product specialist for our 3D printing products, which falls underneath our digital manufacturing group. And I'm also the global additive cohort leader within the company. So I wanted to talk about a few different things today. So first, I want to have a look at some of the AM journey stages, look at the cost knowledge curve, which I have kind of just roughly named it. So hopefully we'll be finding a different name for it at some stage, but it gives a really good idea of where the costs are involved in and how we can start to look at reducing them. Having a little bit of a look at the role of software, and then optimizing that journey that we're going to be introducing. So the typical journey that people go through with additive is they usually find 3 key sections. One is going to be designing. A lot of people, especially if they're coming from traditional manufacturing, they'll be, working with 2D designs. They'll have the blueprints and they'll be doing toolpathing in CNC. One of the challenges for a number of people, which seems like it's something that we take for granted these days, but the design in 3D process is still relatively new. So That's an area where we do see companies starting to really leverage the design tools out there. Next, when they start to actually go into manufacturing, whether it be using a 3D printing bureau, using a additive manufacturing hub like Amtil offer, or any other of these additive part suppliers, they usually go through an external service provider first and then start to in-house some of the production. So that's when they start to do the manufacturing side of things. And then once they have the parts, it's very rare that you'll have a part coming out of the machine exactly as you want and exactly how it needs to be for the end process. So there'll be usually quite a bit of post-processing, whether it's removal of supports or whether it be refining surfaces in certain areas that are going to be part of the assembly, anything like that, or for polymers looking at post-processing for a nicer finish. It is a very wide amount of post-processing that can happen. So these are the three sections that we generally look at, and when we have a look at what I coined the cost curve, the cost knowledge curve, we have a look and we have the part cost on the left in the purple. And as you can see, generally that will start up really high. And the reason again for that is because the design doesn't really take into account additive as the initial design process. It might be a part that's traditionally CNC'd. And as you start to refine that design, make it a little bit better, do some design for additive manufacturing workflows, then once you actually start to do the preparation, it really starts to nail home that, okay, these are some of the things we need to do. Once you know the preparation side of things, you know that there's going to be supports in certain areas, you work to have supportless parts, and that's when you really start to see the cost of these parts going down. So in the amount of effort and time elapsed, you will generally see that coming down. The red axis is knowledge growth. And again, as we mentioned, as you start to do these things, you'll see the knowledge going up quite substantially. The amount of knowledge that's required for doing, for example, design manufacturing in-house and having machines and having post-processing in-house really has a large amount of knowledge requirements, but it really does help to bring the cost of that part down because you are designing, manufacturing, post-processing based on the requirements of that part. This is again looking at a relatively flat part price. This is just because they're developing that part, but we'll go into that in a little bit as well. So again, looking at the design only, going to the design and the preparation of that part, and then in-house manufacturing, we'd like to kind of look at these as the initiating, the developing, and the optimizing phases of the additive journey. And to go into each of these a little bit more, I'll start off with initiating. So again, as we said, it'll be potentially a very new process for many companies, the CAD preparation. They might have traditionally been a 2D design house and they start to do 3D design work. They might use a external service bureau. They will get the quote. They will not have to have the high capital demands of purchasing machine. They get relatively cost-effective parts, and that is again a physical part based on the original design that they just had in their PC. So this is a really great way for them to have a low risk, high return initial engagement with additive. Again, they probably won't have parts that are looking as complex as this. It might be, relatively basic jigs and fixtures that are not specifically designed for additive manufacturing. So as they start to get better with this process, they will, for example, here we can see some latticing. There will be some optimization of that design, whether it be topology optimization or generative design, and it will really help them to reduce the costs because the material consumption is a lot less, and that will help to reduce the costs. So based on that, we'll look at topology optimization, reducing some of the costs, some latticing to reduce the costs even further. Then once we go into the developing phase, this is when they start to be a little bit more involved in the manufacturing process. So this would be more like you're developing, you're designing the parts, you've got very optimal designs coming out, but you're also starting to do some of the support generation, or you might do some of the 3D packing, or some of these things that are a little bit more high value in that additive journey. And that will mean that you start to see a lot more results from not just the design, but also the basic build preparation helps you to better optimize these parts. You'll generally work with a service bureau that's a little bit more hands-on. So rather than just taking an STL, throwing it to the company that's going to manufacture it for you and having them do it, you'll have a bit more of a conversation. So It might be some consultation with that service bureau. They'll create the part with you, and then you will have a relatively optimized part that's going to be at a relatively cheap price. Once we start to go into the optimizing side of things, you'll start to see companies getting machines in-housing these capabilities. And once you do that, that really starts to be not just a direct one-way arrow, but you'll have a really strong feedback loop between the manufacturing and the design teams. This is when you'll start to see some very advanced support creation, which again reduces the amount of material consumed in the generation of supports. It also really helps you to optimize the post-processing capabilities as well. Some of the other things you'll start to do is you'll have specific control over tool pathing. You'll be more focused on optimizing the speed of manufacturing. You'll be you'll have a lot more pressure in making sure that the throughput of the machine is going to be as optimal as possible. Expensive machines, you need to make sure that you're getting the best out of them. Some of the next things that we'll start to look at is, instead of just looking at lightweighting and some of these other capabilities, by understanding the deeper benefits of additive manufacturing, it won't just be lightweighting, but I like to call it lightweighting +1, which is not just making sure that you're reducing the amount of material consumed, but you're also introducing a new function, whether it be high thermal efficiency, whether it be optimal CFD flow rates, anything like that really helps to make that part a lot more valuable. But you also have that feedback loop, so you're going to be bringing in a lot of that information back into the design process. That also does knock on with quite a lot of the effects of post-processing as well. So when we have a look at the additive journey, we generally see that there are 3 key pillars to the success. Hardware, of course, you're going to have a machine at some stage. Otherwise, you'd be relying on external machines, which is still part of the hardware side. Looking at the different materials, again, there is a huge portfolio of materials that have been released over the last 5-10 years, determining which is going to be the best one for you. And if you have a very unique application, it might even come down to you need to manufacture and create a recipe for a brand new material. So that could be part of the 3 pillars of success that you'll be looking at. And then the one that I'm more engaged with is the software side of things. So we're going to kind of focus on the software aspect of the additive journey, and hopefully we can look at how we can use software to optimize that journey. So to kind of put a couple of product names that we usually work with to each of these different stages, we would look at initiating products such as Fusion 360. In the developing and optimizing phases, we'd be looking at a product such as NetFab, which is a little bit more of a professional tool for 3D printing preparation. So when we have a look at the design processing, so we have a number of different ways of designing. Generally, it will be design exploration. We'll look at having multiple different concepts. From these different concepts of a design that you have created, you'll go into validation. Once you've completed the validation, you're going to production of that part. Anybody that's done manufacturing will know that it's never this clean. There is always a number of issues with, okay, this concept's really good, but when you take it into, for example, simulation, you'll see that there is not going to be a way that that's going to be a successful part. You might take it to the manufacturing team. They say, we can't do these kind of undercuts in CNC, so we're going to have to use a different technology, take it back to the drawing room. And you're going to have a lot of these concepts having a lot of back and forth, and that really adds to the amount of time that it takes to get to market. So that production relatively is a slow process. With a lot of additive at the moment, we're taking this already defined production part. So for example, something like this. And when we do want to take it to additive, quite a lot of people are using topology optimization as the key way to take that into an additive environment. So taking the part that's currently being produced, removing material from certain sections of that part and producing it additively. One of the key issues that I find with this, and one of the reasons why I don't particularly like this method, is because, for example, up until this section, you might be looking at doing this with CNC. The very, very last step is when you start to bring into additive, but it means that every section of that concept development phase and checking manufacturability and all these sort of things, again generally going to be done with a different technology. So I'm not a massive fan of topology optimization, and this is one of the reasons why I have been working quite heavily with Autodesk, is because we generally see that there is a gap in that capability. We want to be bringing this additive produced part knowledge back into this initial phase of concept generation. And this really helps us to increase the benefits of the parts that we're going to be designing. So one of the things that I have been working with different teams is with a technology called generative design. It's built within the Fusion 360 product. And to give you a bit of an idea about what happens is we take multiple different types of materials. It's not just a single material. We have multiple different manufacturing methods, and we get multiple different designs so that the engineer doesn't have a one design to look at. They have multiple different materials, multiple manufacturing methods, and multiple designs to weigh up the trade-offs and to understand which is going to be the best technology for them. So when we have a look at some of the expectations around the parts that come out, so for example, each of these parts that come out, they're going to have information about cost. So we'll have the part cost information here. It will be based on different materials. It'll be based on different manufacturing methods. And from this, we can actually have not only a good understanding of what this will entail to manufacture this alternative, we also have a fully pre-simulated result. So this really gives us an idea of where the areas of stress are going to be. This part, if we are interested in manufacturing, this can be brought into a direct CAD environment, so you can do any post-processing that you need on this. And this really helps to reduce some of the stresses of using mesh, which is one of the key issues in topology optimization. The other thing is, of course, because we have taken into account the manufacturing method during the initial development process, we can have a look and weigh up the alternatives. So for example, if we wanted to look at a 2.5 axis CNC result compared to an additive result, we can see that there are a range of different factors. The additive result is the best in terms of the lightweighting, but because we have the different information around safety factors and cost, we can tell that, okay, maybe that might not be the best design. And even though this is an additive webinar and we are looking at evangelizing and building out the additive industry in Australia and New Zealand, one of the key things that we want to make sure that people don't do is put the wrong parts into the machines. With the costs being so high, it can lead to people having negative images of additive manufacturing. So I always say, make sure you have the right part going into the right machine using the right material. And again, that is a relatively large amount of information that needs to be known. So an event like this, where we have, for example, the AM Hub, as well as some of the research teams, such as the team that Alex is working with, I think that it's a really great way for us to build out this muscle. So when we have a look at the comparison to what we were looking at before, instead of having multiple different concepts, which you then need to do validation on, each of the results that come out of generative design are already validated. They've already taken into account the manufacturing constraints, and then you can just choose one and take it into the make environment. So compared to the previous design process, this really does help to increase the productivity and reduces the time to market. So that's on the design side, but when we have a look at the build preparation side, it then adds a little bit more complexity. So we have the design and CAD, which is where we're talking about generative design, CAD, 3D CAD design, all these sort of things going to phase one. Then the general workflow would be that you would import a part, you would do further optimization, whether it be latticing or whether it be any further optimization of that geometry. Especially if you're working with STLs, a number of the time you'll have to do some relatively heavy repair work. If you're developing a part within CAD, it's usually all right to export it as STL, but if you're working with, for example, a scan geometry, quite a lot of the time you will need to do repair on that geometry. Then you will pack the parts, whether it be plastic and doing a 3D pack, or whether you're working in a metal, which is generally a 2D pack, sometimes a 3D pack. You can then pack these parts, making sure that you have as many parts in that one build as possible without overfilling it. Taking it and, for example, doing any offsets that you might need to do for post-processing. This might be adding a little bit of offset to the down skin so that you have some material to remove when you're taking the supports off and doing some polishing. Then adding the supports. So again, especially for metal 3D printing, you will need to have some of these supports. Again, not the best thing because it does add quite a lot of post-processing. It takes up material, it takes up manufacturing time. So we want to reduce as much of this during the design process as possible, but it is just a necessary evil of the technology. So this is part of the workflow that we need to be working with. Then we'll take it in for toolpath optimization. And then one of the other things that we have within the software is simulation for metal processes. So you can see if this part is going to be successful, if at this orientation with these supports and these parameters for the toolpath, is this part going to be successful? After confirming that, or after confirming that it's going to fail, you can take it back and iterate in a digital environment rather than having to get the machine to do the fails for you. You can resimulate and send it to the machine. This really helps to ensure that successful parts coming out of the machine. And again, that does tie directly back to the ROI of that machine. So if we're having a look at a part, for example, this part, which is in the purple, we want to be manufacturing this. We don't really know which is going to be the best iteration. If I have just purchased a metal 3D printer and I don't really know what the best orientation is going to be, generally, you'll see people doing some trial prints. You'll see a number of different failed parts, and then they will start to understand as they go along which is going to be the best way of manufacturing this part. Just quickly, maybe if people in the chat can post which they think would be the optimal way of manufacturing this part, it would be good to see if there are some inputs from that. So if you can chuck it in the chat what you think. I'll give it maybe 10 seconds just while I have a sip of water, just to see what people think. All right, so we've got a couple of different feedbacks and we have 4, 2, 3, and to be honest, it's very hard to say. If I said, okay, there is going to be one best solution, you would need to be giving a lot more information to understand what the best solution is. If we're looking at best solution for cost reduction, if we're looking at best solution for post-processing reduction, if we're looking at reducing distortion, if we're looking at effectively packing the build, there is a lot of things that can and should be considered when you're manufacturing this part. So some of the things that we might look at, number one, if we've done the simulation of this, we can actually tell what the amount of distortion will be prior to the build. So number two, while it does have some distortion in this area, the engineer might look at it and say, well, that's a relatively sacrificial area. I don't mind if there's distortion, I'll just CNC it anyway. You might be looking at, okay, there is a very nice amount of distortion reduction in 3 and 4, but when we have a look at it, you know, fitting 6 and 7 on the platform, if we have a short lead time, we might need to be fitting 8. In which case 0.5, similar area of distortion, we can look and actually do a compensated geometry, which takes into consideration this distortion and reverses it so that during the build process, any areas that are going to be, you know, shrinking actually already expanded out so that you do offset that distortion during the design phase. So again, there is no correct answer. So everyone was a correct answer, but it really comes down to which is going to be the best option for that manufacturing technology. So if we have a look at it in practice, so for example, this is one of my more favorite examples from FIT, which is a service bureau in Germany. If we have a look at this part, a customer came to them and said, we want to have 1 or 2 of these created so that we can do some product development. It's just going to be used for prototyping, so it doesn't need to be fantastic, but we want to have it as is. The part was going to be made in steel. It has a lot of supports, it has a lot of weight, and it's not very practical for additive, but if it's just going to be in prototyping, you want to have it exactly as it looks during the actual manufacturing process. So that's going to be suitable. If they said, now we want to do a short run of 100, you might look at saying, okay, well, we can do the design optimization. We'll have a look at it. They've done some basic topology optimization, understood, okay, this is going to reduce the amount of weight in the part. it's going to also heavily reduce the amount of supports that are required in building this. So it's been a relatively positive engagement. But once they say we need 1,000 of these, there is still a lot of post-processing that happens on each of these parts. So what they might look at doing is, for example, going to the final part, which is taking into account post-processing, taking into account manufacturing requirements such as supports. And what we've done here is we've gone from 315 grams of supports down to 3 grams. And the majority of these supports are on the base of this part. So once you wire cut that off, you're going to have a relatively easy job in doing the final post-processing. So again, taking it from the initial design that doesn't have any additive knowledge going into it, bringing in some basic design knowledge and optimizing of that part, and then actually having that knowledge building in some of these areas that would have traditionally been supported into the design and using that to remove sections of material from other parts of the design. This can really help to reduce the overall costs because, again, the post-processing is going to be as light as possible. So again, so when we have a look at this graph that we had a look at before, so what we're looking at doing with software is, again, trying to move this and shift this, do as much front loading of this information as possible, right? So taking the design only, bringing the build preparation in as quickly as possible, doing heavy iterations within a simulation environment rather than taking days to get a part out of the machine. You can have a digitally simulated part relatively quickly, and that really helps to bring in that understanding of design and manufacturing. Even if you don't have a machine in-house, you can still understand the process a lot more clearly. The other thing that we do also want to look at is trying to build out that part price. So instead of having a price that you're going to be charging that's a flat rate, by including a number of different functionalities into that part, by optimizing that design for lightweighting, again, the part price can go up because you're able to charge more because it is going to be delivering more. So that's a very quick introduction to what we're doing. I'm really looking forward to some of the QA at the end, so please stick around and I will pass it back to Anna, who I believe is going to introduce Alex.
Yes, thank you very much for that, Peter. That was really interesting. So please, everybody, fire up your questions for Peter and let's put him in the hotspot later. And last but obviously not least, I'd really like to hand over to Alex Kingsbury from RMIT, who's going to talk about how the impact and research in your additive journey and how it can help. So with no further ado, I'd like to hand over to you, Alex. Thank you.
Thanks, Anna. Okay, just showing my screen. Everyone can see that okay? Yes? I assume yes.
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 Great, thank you. Thank you for having me. Lovely to be here. I'm going to just jump right into it. I've got a couple of slides I want to get through. So here's me. I've been working in additive manufacturing for about 10 years now. I'm a chemical engineer, but I moved into additive manufacturing through metal powders as I was working quite a lot in those when I was at CSIRO. And really, I feel like my career has almost progressed with the progression of additive manufacturing. So I ended up my time at CSIRO as the center director of our additive manufacturing center. I spent a couple of years in industry as a consultant in AM, and I got to work with a lot of really amazing companies, both big global multinational type companies right down to small SMEs. And what we were really looking at a lot of the time was around how do we get into additive manufacturing and how do we make it work for us, more importantly. And I am now at RMIT as an industry fellow. I lead the engagement theme for our research centre. And in my spare time, I'm also a PhD candidate. So that's a little bit about me, but essentially really where I fit and feel very strongly about is about really translational research that makes a big impact on Australian and worldwide companies. So I love seeing commercial outcomes for research. So I want to just take us through a little bit about the 7 types of AM, and John did a wonderful job of describing in detail some of the processes of additive manufacturing. I think the really important thing here is just to remember or at least appreciate that additive manufacturing is a whole different type of a host of different types of technologies. Okay, so it's like a collective word that is a summary for lots of different types of technologies, and there's quite a number, as John has explained. And really the only loose definition holding it all together is that we're making objects from 3D model data, usually layer upon layer. But there is quite a number. There's quite a lot of different types of machines, different ways of joining those materials, different materials themselves. And as a result, we have everything from, you know, your small hobbyist little printer that you might go and buy at Aldi, for example, right up to, you know, a multi-million-dollar industrial grade machine. So, for example, one of the issues around using trade names, I feel as well, is that it can be a bit confusing for people when you're just wanting to find out more information. So the field of additive manufacturing has been sort of plagued by these trade names. And what it does, and I've noticed this a lot when I work with people who are looking at AM, is that it just actually confuses the issue. So you go, oh, well, is, you know, for example, you know, FDM, is it, it's actually material extrusion. So that's what I've got a picture of up there. And that's what most people know as being, you know, your classic 3D printing. Yeah, but when we have these issues in trade names versus standard names, we're actually talking about the same thing, but we don't realize it. And that just leads to a lot of confusion, and also it doesn't really help people get to the information that they need to really quickly. So I'm on the AM Standards Committee for Australia. So of course, this is one of my pet topics, and it is something that's really still really developing. It, you know, lots of people use all different types of trade names, but anyway, 7 different types, and those are the official names. I'm going to talk a little bit about Australia and New Zealand because I think it's really quite fascinating. I guess having been in this field for 10 years, I've been able to watch it really unfold. And that's a little map of all of the machine capacity that we have across Australia and New Zealand. There's always one that I'm missing. So I've got on my next slide here all the names. But yeah, there's always one that I'm missing. If you see one, please let me know. But commercial and academic so providers have been noted here. And as I said, it's machine capacity. There's always a whole lot more that supports additives that's already been touched upon, which is, you know, materials providers, software providers, post-processing providers, all of those types of the AM ecosystem aren't in this map, but this is really machine capacity. If you need something made, where can you go? Or if you need some support, where can you go? Couple of notes about this. You'll notice that there's a lot of activity around Melbourne specifically, and particularly on the commercial side, there's a lot of activity around Melbourne. I don't really know what the reasons are for that, other than it was really RMIT University that I worked for and CSIRO that I used to work for that were the first big entities to get into these machines. There was a company actually in Sydney who was the first in Australia to buy a machine. But after that, it was really RMIT and CSIRO that pushed forward with this technology. And it's really flowed on from there. So that's why, if I could take a guess, that's why I think there's quite a lot of activity in Melbourne. It's been because very early on, there was significant investments in the technology, especially on the metal side, actually. And another trend that we also see is, and this has happened, you know, not only in this region, but also worldwide, is all of the universities go and buy these machines, and then they'll buy, you know, 1, 2, maybe 3 of these systems, and then it flows into the commercial world. So, you know, once a system sits with a university or a research provider for long enough, there's, generally speaking, and I certainly speak from my own experience here with RMIT and CSIRO, we have a lot of industry partners and a lot of industry people through. So that starts to raise the bar in terms of awareness and understanding the technology. And then you start to see the technology filter through into the commercial world. And yeah, like I said, that's been a really big focus of my career in general. And it's something I'm quite passionate about. So in Australia, we have a number of service bureaus in the commercial space. We also have, really interestingly, a couple of machine providers, or what we call OEMs, right? So these are people that actually make the machines. And in that space, we've got some interesting players, people that make machines and also systems integrators. So we have 2 in cold spray space, we have 1 in the wire arc space, we have another in the powder bed fusion space. So you know, Australia in particular on the OEM side is actually really sort of pulling its weight in an interesting way. Anyway, I'll move on. That is the list of all the players. But yeah, like I said, you can see that there's, you know, probably disproportionate amount of commercial activity happening in Victoria. I'm a Melbourne person, so I suppose that makes me proud. But anyway, we'll move on. I work at RMIT Centre for Additive Manufacturing. That's a couple of pictures of the Advanced Manufacturing Precinct building where I'm based. We have everything in additive manufacturing, I think, really that you could ever want. We have metal printing systems, we have polymer printing systems. On our polymer side, we have hobbyist printing systems, and we have industrial grade machines. We have 3D scanning and metrology. We have wire cutting, we have testing, we have any software package you could possibly ever want. So we're really very, very well equipped. And we also actually have you know, machining as well, which, you know, goes hand in hand with additive manufacturing often. So we really have everything that you could really want to get going and get started with additive manufacturing. It's been a very big investment on the side of the university. The centre itself is, you know, up to the tune of sort of $35 million in terms of investment. And like I said, you know, it was about 10 years ago that the first machine arrived at RMIT. So RMIT has been working in this space for quite a number of years now. On the research side, we do some incredible work. I won't talk too much about that today, but yeah, have been able to form some really important strategic partnerships. And this is really where I think we perform very strongly, because our strategic partnerships, they aren't just about doing projects together, although that's a feature. It's really about implanting people from RMIT into those companies and people from those companies into RMIT. So for example, someone from Ford is one of our adjunct professors at RMIT. We have people from RMIT going and doing you know, internships and so on into these companies. These companies will sponsor sometimes a PhD project and a research project. They might sponsor student projects as well. So yeah, and often we might sit on their, for example, technical advisory board. So there's a lot of cross-pollination that happens between us as a university and these companies. And in my opinion, that's really the most fruitful way in which to engage with research, is do it on a very strategic level. So, you know, for some of our very important players in our strategic partnerships, we've literally been orienting our purchases around what their research needs are. So that's a very powerful thing to be able to do, to be able to leverage a university in that way. But likewise for a university, it's really great for us to be able to know what our partners are thinking and doing in terms of their, you know, roadmaps, their technical roadmaps, and how we can support them properly. We have essentially 2 types of projects within the university, and you'll find this is really common across pretty much all universities. And they're basically either research projects or capstone projects. And I guess there's one a little bit in between, like that I mentioned, which is sponsoring PhD students or postdocs. But essentially those are your two options. Research projects are much more comprehensive and also bigger budget in general. You tend to have a full-time researcher, so fully graduated, you know, post-PhD researcher working on your project. And as a result, we can get the project done in a very short timeline. There is funding available, and the funding in Australia, I have to say, is second to none. I've been around in this scene for a little while, and I know that other countries don't have the kinds of funding available that we do in Australia. So, you know, we're very lucky to have some really positive government support, and that has been, across a number of different governments as well. But anyway, moving on, the R&D tax concession is probably the most common. You do have to pay for your project up front, but then you can claim it back in tax. But it's, yeah, I think it's 60-40 now, but most funding schemes are about 50-50. We also have a number of CRCs that are floating around. We also have voucher programs, one of which John mentioned, the Build It Better voucher. And, I have to say, in my opinion, those voucher programs are fantastic because it means that you don't have to, particularly if you're a smaller business, you don't have to stump up the cash and then get it back later. You're able to just access those vouchers as you need them and have 50% of your project needs paid for by the government. So generally speaking, a pretty supportive ecosystem here for research projects. The other one I want to talk about a little bit more is capstone projects. And so those are a really good way for, again, just thinking about SMEs. So, wanting to get involved in additive manufacturing, using a capstone project is a really great way to go. So at RMIT, we obviously do research, but we also have teaching and learning. We graduate a whole lot of students every year in engineering and also across other schools as well. And at the end of in their final year, one of the requirements for students is to do what's called a capstone project. This is a group work project. Ideally, we love for these to be sponsored by an industry partner. And so what that means is that an industry partner comes to us and says, hey, we'd like to investigate X, Y, Z or prototype this. There's got to be some level of inquiry and open-endedness about it. It is like a mini research project, but throw your problem at us and then we go, okay, we're going to assemble a group of students who are in their final year, so they're nearly graduated. You have an RMIT supervisor who guides them through the process, and what they do as a student group is they look at what you've proposed to them and they go, okay, we can see what the scope is here, we're going to define it and we're going to craft some questions around what we want to ask, and then we're going to develop a plan for addressing that and do that. And so one of the advantages of this, the capstone projects, is that they are free, which is wonderful for many people. They are, in terms of timeline, a little bit longer generally than a research project, depending on the scope, of course, but you've got to be patient with the process. We start them in about February and we finish them in about November. And that's really the timeline that we work to. So they don't go any longer, they don't go any shorter. It's got to be that sort of, academic year length. As an industry partner, you keep the IP that's generated, which is really, I think, a really fantastic part of being an industry sponsor for a capstone project. So there's no hassles about, where the IP goes and what happens. And the only other thing about it is that you've got to be okay with the fact that the work is published. Having said that, the students obviously write a report which goes into the RMIT system. We don't publish that openly, but what we do have is a poster session at the end of the year where they get to stand up and talk about who they worked with, what it was that they did and what they achieved during that project. Some companies get a little bit worried about that, but the thing is it's actually a pretty basic sort of publishing. It's not publishing every single detail of the project, but anyway, that's the gist of it. As an industry partner, you are it's sort of expected that you spend about 30 minutes a week with the students. You don't have to. I've had industry partners that spend a lot less. I've also had industry partners that spend a lot more. But it really depends on what it is that you want out of the project and how much influence and guidance you want to be able to give the students and how much you want to guide the outcome as well. So yeah, those are our two types of projects. I'm going to just take you through one research project very quickly, which I just think it's such a fun one to talk about, and everyone always likes to hear more about this one. This is a research project that we have with Stryker and a number of others. It's called Just-in-Time Implants, and the idea here is that we're printing implants, orthopedic implants, and it's generally around tumour removal. So you'll see on the top left there, there's a large tumour. Now, to remove that, you really need to remove all the bone. The top right is the implant replacement. And you'll see that there's a lattice structure through all of that implant. And the idea with the lattice structure is that we have an algorithm that we've developed at RMIT as part of this research project, which tunes the cell size of the lattice structure according to the kind of bone that it's trying to mimic. So the important thing about bone is you have two types. It's like a bone is essentially like a composite material, and they have different Young's modulus. So you really want to be able to have a lattice structure that mimics the Young's modulus of the kind of bone that you're trying to replicate. If it's too weak, it could fail prematurely, and if it's too strong, it can crush the bone, unfortunately, and it's not a successful implant. So we've been able to do that. Now, moving on, if you look at the bottom left, this is really where our work has gone to the next level, because what we've been able to do is integrate this project with a whole robotics investigation and a tooling investigation, which means that we can, instead of doing straight cuts like you see on the top right, we can now do conformal cutting, and we can also do conformal implants as well. And then, you know, again, implementing that lattice structure algorithm to directly mimic the bone that it's supposed to be replicating. So this is a multi-year project. Stryker, you would have seen them up as one of our strategic partners. They very much are. With the GM of Stryker in Australasia is on our industry advisory board. So yeah, and this project has also been, you know, funded but also topped up. So it's one that's continued actually longer than we thought, because Stryker was so happy with the outcome. So we're very proud of this one. But yeah, this is a multi-million-dollar project. So not really in the realm of most players in Australia. The capstone project that I wanted to talk about is one that we did with Feather. So this is actually, you know, a pretty simple idea. It was done with an engineering student called Benjamin Gregor, and it was supervised by David Taylor, who's also an industry fellow at RMIT like me. The idea was quite simple. It was, hey, let's think of designing a mount that, rather than having all of this instrumentation on your bike, you've got your Garmin, your light, a bell, you need space for batteries, there could be a reflector, that kind of thing. Let's put it all into one single mount and minimize all of this complex instrumentation that you might have on your bike. So Benjamin was an amazing student, and he mocked up a concept for it. And through the course of the capstone project, he went through and did the design. So you can see here, he's done some initial prototyping. This is all on our machines. And you can see that he's got a couple of different designs that he was thinking of as prototypes, and then was able to print those out in plastic as an initial prototype and have a look at them. Then he moved, once he was happy with the design, he moved to a simulation where he was able to have a look on the finite element analysis of what's the stress patterns through this Garmin, and is this thing going to hold up in real life, before we go then to physical testing. So of course we've got all the testing equipment that you could possibly want, and he was able to do some testing. You'll see the bottom left there, that is a Garmin mount broken or bending. It's certainly broken in the bottom right. So yeah, just making sure that this instrumentation mount is up to the job. And the final result then is, as you can see there, was this a beautifully designed thing. And yeah, look, I'd love to say that this went into production and that it was a raging success for Feather. I don't think it was, but I think the point is that that Feather was interested in what this might look like. And they were able to just throw that project at RMIT and say, you know what, just go for it. And actually, in the end, they weren't especially involved in this project, but what they got was a really great result and was exactly fitted the bill of what they were after. And from the student's perspective, he was able to go and do a whole host of different things, you know, from testing, simulating, and designing, prototyping. he was able to go through that whole entire workflow. The other thing that, I think is important, because it was mentioned in John's presentation and also in Peter's, and both of them mentioned, issues around, build orientation, support structures, post-processing. These are all things that we do through these projects. So these are all things that we want our students to learn, but then you as an industry partner get to observe that whole process as well. And no shade to service bureaus, but sometimes if you work with a bureau, they're going to be pretty secretive around the way that they might orient parts or manage support structures or manage their post-processing. Whereas as a university, we don't care. We've been operating these machines for 10 years. We know how to use them, and we're very happy to share that knowledge. So that's all part of the project. So it's not actually, as much as design and prototyping and testing is a really big part of the project, actually ironing out some of those issues around build orientation, post-processing are really important, and they can actually kill a project. You can have the greatest design ever, but if you're not being able to stack a build efficiently, or the post-processing is taking hours and hours and hours, then that writes off your business case. So these things are important to work out too. Okay, so just finally, please feel free to get in touch with us. We're pretty accessible. Follow us on our LinkedIn page. We're RMIT Centre for Additive Manufacturing. We put posts up of a lot of the research that we're doing and the projects that we're working on. We try and make it as fun and interesting as possible. We also have a website where you can go and see all of our latest news, our latest projects, and go and have a look at that. And also please feel free to email me as well if you're interested in any of what I've talked about today. So that's me. Thank you very much. I'm looking forward to this panel.
Thank you very much for that, Alex. It's so interesting seeing what's happening in cutting edge places like RMIT. So I don't know if the speakers can put their video on. We've had quite a few questions actually, so please feel free, the audience, to put any other questions in there. So the very first one we had was from Simo from PLM Hive, and he had a question for John. He said, looking at the AM scene in the Asia Pacific region, what are the main competitive advantages of local AM capability in Australia in terms of commercially established AM technologies, considering the number of challenges that you presented earlier? I think you're on mute, John.
Okay, that's it.
That
works for me now. Yeah, I think very good question. I mean, the main AM technologies, and if you're talking metals, is of course SLM is the biggest one that's been taken up. As we know, we've got our local company Speed 3D that produce the cold spray machines, and they're doing exceptionally well with especially in the defense area, and they're now exporting into South America and that, so they're doing really well. I think the SLM technologies is the ones which we've been doing a lot of work with the BIP vouchers and that over the 2.5 years. And I mean, we've worked in tooling, we've worked in the mining area with it. And this, when you talk about some of the service bureaus, I think one of the major service bureaus that's been used through that is, of course, Amiga Engineering over in Tullamarine. They've done a lot with tooling for injection molding, which is one of the big VIB vouchers that we did, that they did a prototype tool first. And this had very thin sliding cores, but the beauty with that, of course, was around conformal cooling of what they could get into the tooling to manufacture the products. I mean, the tool cycle times were reduced by nearly 40% from a traditional tool to the additively manufactured tool. Of course, the expense was reasonably high, but the company indicated that from the prototype tool, they've now gone into a full production tool, which they've manufactured again additively. So obviously they're seeing the benefits of that over the time. Several other areas, of course, have been in the mining and construction. Again, it's been mainly a lot to do with the metals. As far as the polymers are concerned through the BIBs, the polymers are basically being used to manufacture a lot of the prototypes. And like Peter presented, it was all to reduce time to market for them of getting product to the market. And they also utilize the polymers to do their first off runs as well. And I think the main one that I think showed, I suppose, the most use was, of course, the HP with the multi-jet systems. They were the big ones as far as producing parts. I mean, we're still producing parts now, and there's another company that's produced a COVID testing unit, which they're using quantum dot in, and that is showing some really good signs of moving through now to the future. The US are just ringing them every week. They're wanting these 100 samples to come in so that they can start to run testing and get it through FDA over there. Hopefully I've answered the question okay. Again, mainly SLM, and it's been utilised mainly in Victoria through the Victorian service bureaus. We have service bureaus all over the country. And of course, as Alex showed, New Zealand, I mean, RAM 3D is a huge one, using the Renishaw equipment. Renishaw, of course, are being used by Bastian Cycles, producing their unique push bikes for market. Not cheap, but a really good push bike. Yeah, so yes, hopefully that's answered the question.
Great, thanks, John. So I've got one here for Peter. With the vast majority of people designing based on baked-in knowledge of subtractive manufacturing methods, is Autodesk planning on trying to educate its users on how to design for additive? It's a big shift in mindset, and each AM method has different requirements, advantages, and limitations.
Yeah, absolutely. So I think that there's a number of issues in the design process, and exactly as you said, people are generally thinking straight lines. When additive, you're going to see more issues with straight lines than you are from curves. So one of the things that we like to do is not necessarily educate, but bring quite a lot of those capabilities into the software. We, of course, have a very strong education program where the software is then, of course, backing some of the teachers and some of the research teams that are going to be implementing these. So they do a lot of the education around the software capabilities. But one of the things that we like to do is, especially with generative design, I think that it's a really great way to add additive into the mindset by, it's literally a single checkbox. You tick the checkbox for additive manufacturing, you put in some of the additive build constraints, and while you're looking at all of these other results for, you know, CNC casting, you also then have the ability to look at the results for additive. So this really helps you to design for additive because it gives you an additive solution, even when you're not necessarily looking for it. And that's generally some of the time we do see that as being one of the key things that is challenging for people, that they just don't know what parts to actually apply additive to. So the parts screening process is incredibly challenging. And then once they actually find that right part, then understanding whether it's an additive part or not does have that challenge. So in the slides, I kind of showed that part where there's the 3 different manufacturing methods and whether or not additive was going to be the most successful one. It helps to kind of implant that information in there. The actual specific design for manufacturing is a lot more involved. But we are looking at not just looking at the FE-based optimization for lightweighting, but we're also developing algorithms that are going to be using CFD optimization for designs. It's going to be thermal optimization of designs in the generative workspaces. We've already have delivered a project with Panasonic on automating of cooling, conformal cooling channels in molds. So you put the inlet, the outlet, have the original design. It creates the optimal internal cooling channels for that part. So we're really working on developing some of these plus ones, which, as I mentioned before, it's lightweighting plus actual functional benefit of having additive in the mix. So it's not necessarily that we're going to go out there and educate, because we're not really an education team, but we do provide the tools that are going to help the educators to really drive home some of the additive benefits in the design process.
Thanks, Peter. So I've got one here for Alex. In universities, how often are engineering students intimately exposed to metal printing? And if they aren't, what sort of things need to change for them to get more hands-on experience?
Yeah, I suppose so. For starters, I know the question was about metal printing, but just on the polymer side, they do that in their first year. So, you know, there are actually a lot of really valuable crossovers between polymer printing and metal printing, just in terms of the AM workflow and understanding that, and also in designing for it. Yeah, there's some nuances between metal and polymer for sure, but you know, just even just having that mindset change around design is really important. And so you can take students a very long way with just polymer printers. And you know, a big part of the reason why we use polymer printers, of course, is because they're so much more accessible and lower cost. And if you break one, it's okay. So we start them off in first year with that, and then they go through their you know, usual. You know, and I'm talking kind of typically mechanical engineering, manufacturing engineering that we offer at RMIT. They go through their usual coursework, and then it tends to be that they come back to additive in around final year, and that's through the capstone projects. And there are definitely some students that are very sort of inclined towards 3D printing already. They might already have printers at home, or just they're just really interested in it. And so we do tend to offer quite a lot, particularly in the metal side, for capstone students. Now, the question was about hands-on experience. I'll just note that, so if you want to be hands-on with a metal printer, you really need to go through some extensive training. Metal printers, and I'm talking specifically about the laser powder bed fusion printers here, but generally speaking, metal printers, they're industrial systems, and there are a significant number of safety issues connected to them. So you really do need a lot of training to be able to use and operate a metal printer in a safe manner. So I don't personally think we should be getting our students to use or be hands-on in the machine operator sense with a metal printer. That's really, that, you know, I hate to say that's the job of industry, but that is the job of work experience, right? So doing something like an internship with a metal printing company and getting your hands-on experience that way, great. But you will find that even a company is not willing to take on a student for an internship and train them up in being able to be proficient with metal 3D printing, because it takes a significant amount of investment. So yeah, the capstone projects are the best way to do that. And likewise, you do get to go, a lot of these students, they really get to go through, again, the AM workflow process steps, and they do get to be side by side with the machine operators to be able to print their stuff for whatever it is. And they do get to go through, if I talk about, say, you know, the Garmin mount, Benjamin was able to work with our technicians to be, like I said, side by side, watching the thing being printed, seeing how the machine is loaded up and prepared, seeing how it's unpacked, all of that, just not hands-on, because we really can't afford the safety issues with that. And you'll find that in universities, but you'll also find it in industry as well. And you'll find it in research institutes. For example, I'm not allowed to touch the metal 3D printers, right? Because I don't have that training, and I am not the technician that operates the printers at the university. So that's the answer to my question. I think, so I guess, yeah, in summary, I don't believe that needs to change, But what I would love to see more of is more metal 3D printing projects as capstone projects, because I think that those are so valuable in getting experience with any kind of printing, and actually any kind of work experience is fantastic for students.
Thank you, Alex. So probably got time for maybe one or quick two more. One from Alex Lubansky to everybody. We're doing a bit of AM prototyping, but we'll later be wanting to do very high volume manufacturing, which will probably be using traditional manufacturing processes. What do you see as some of the biggest pitfalls in that transition? So open to, I guess, John, why don't you kick off with a... Got to put yourself off mute.
I know, I got that. Yeah, good questions. I mean, a lot of the people we've been dealing with, they're actually moving from doing their prototyping and doing first runs and that out of additive, and then moving into traditional manufacturing, such as injection molding. And I talk about injection molding because that's my background as such. So a lot of them now are looking at still utilising additive in developing the injection mould. The bolster and everything still remains the same. So it's all traditionally manufactured and still cost effective to do it that way. But they're now looking at how they can reduce cycle times within the tooling, and also the times of getting inserts built and made to put into the tooling. So, you know, some of the pitfalls, of course, of moving away from additive, if they've additively manufactured inserts and they put them in, of course, they can have issues with such as shrinkage rates of the part that's being molded and they've just got to manufacture further inserts for the tooling. Where the traditional ways of manufacturing, you'll see with a shrinkage rate itself. I know that we talk about with additive that we can certainly determine shrinkage rates, but they're not down to microns, put it that way, as yet. So traditional still has a play in the manufacture of injection molds.
I wanted to say hi to my mate, Alex Lubansky. Thanks for asking that question. Yeah. And I would flip it around a little bit and say there's no pitfalls, there's only opportunities. If traditional manufacturing, we wouldn't call them traditional manufacturing processes are what's best for your process, and that's going to be the best way to produce what you want to and the most cost efficient, then that's what you should do. And so the opportunities are, you can prototype using AM, absolutely, and the opportunities are you can definitely, as John's talked about, use 3D printing for tool inserts and get huge amounts of advantage around that. Many companies will use traditional manufacturing, but then also integrate sort of sub-assemblies that are additively manufactured. I think that it's a fascinating technology. We're all very excited about it, but I think, we all know too that it's got to be used where it makes the most sense. And if you mass manufacturing, it's very likely not going to make sense. And a lot of the time it does come down to part size and materials, and tolerances as well. So tolerance, part size, materials, and tolerances are really critical in terms of real manufacturing. And additive can only give you so much with all of those three things.
Well said, Alex.
Right. Well, I think we've reached the end of our hour and a half, and I would like to, I'm afraid we didn't get through all the questions. So what we might try and do is take some of them offline and see if we can get some answers that we can feed back to everybody. Thank you very much, Alex, Peter, and John, for your time and your expertise and your presentations. And I just hope with everybody who attended that this kicks off some discussions that either with the AM Hub or RMIT or with your Peter directly with Autodesk or your Autodesk partners around additive and what your next steps might be. And I do note that somebody asked if it was too late to do a capstone project, Alex. So no doubt somebody might be contacting you directly offline, asking if they can squeeze in a capstone project this year.
Yeah, just send me an email or just look me up on LinkedIn.
Yeah. So thank you. Thank you again, everybody who attended, and thank you, Peter, John, and Alex for your time and expertise. Really interesting session. Thank you.